Here's the calculations for the monkey and the hunter. I just did a short on this video. Also, you can see my other video on this, the first video I did on this that tells all the logic and how I came up with the idea for everything. And that'll give you some background, so you can see that if you're interested. The reason I'm doing a reshoot on this is because you'll see there's actually quite a bit of calculations involved on this. And for that first video I didn't want to do all these calculations. I just wanted to watch things fall and get a nice parabola. My time increments didn't match up on that, so I wanted to redo it so that all the numbers matched. My frame rate was 0.4 seconds per frame, but the increments I used for everything to fall from gravity was 0.5. So I had 0.4 and 0.5. I wanted to redo it and make everything match. But as for this diagram right here, I used a 30-degree angle here. This scale is a 1 to 10 scale, so instead of 50 by 100 centimeters, this little triangle is 5 by 10 centimeters, so it's 1/10 scale. I wanted to do exact calculations to get a nice symmetric parabola, just because it looks kind of pretty and I wanted to see if I could do it. Break this problem into a couple of big parts. First big part will be the hypotenuse. Velocity of the bullet, travel 100 centimeters in 10 seconds. The reason I chose 100 centimeters is so I could use the whole board. The reason I chose 10 seconds is because I wanted to make it short and sweet. So velocity of the bullet, 10 centimeters per second. I did 20 frames total for the stop motion. The reason I did 20 is because 10 was just a little too little of effort, and if I did like 40 or 50 or 100, that would have been too much effort. So the whole thing will be shot in 10 seconds. That's 10 seconds for 20 frames, 0.5 seconds per frame. That's actually what I did on the second run. On the first run, I made it go even faster to 0.25 seconds per frame. I wanted to speed it up just because I thought it would look kind of fun. Next up, bullet travels 100 centimeters in 20 frames, so that'll be 5 centimeters per frame. That's how I know how much to move the bullet up with each frame. Notice the black marks on the gravity bar. I'll call it the gravity bar because that's that brown cardboard thing that falls, and it kind of shows you where everything is in relation to gravity. Now for the y-axis, the fall was 50 centimeters in 10 seconds because 50 centimeters is the opposite leg on the triangle. 10 seconds, like I said, is because I didn't want to make it go too long. So that means everything will fall at 5 centimeters per second on average, but keyword there is average, because at the beginning, when everything starts accelerating with gravity, things will barely move. And then as the seconds tick by, those gaps, or those increments, are going to get farther and farther apart, and it's going to move really fast. Good old 1/2 at squared equals distance. So 1/2 acceleration, and then the time will be 10 seconds for everything to happen, and it'll fall 50 centimeters. Solve for acceleration. That gives an acceleration of 1 centimeter per second squared. I take my acceleration from my fake setup here, my fake gravity, which is 0.01 meters per second squared. Divide that by real gravity here on Earth, 10 meters per second squared. Notice the units will cancel. This is meters per second squared, so I'll be left with just a number that is unitless. That'll be 0.001, which is 1/1000th gravity. I initially planned to just run it at this speed, but then I sped it up for the first run to make it go twice as fast. So the first run was 1/500th of gravity, and the second run was 1/1000th of gravity for acceleration. I couldn't find any astronomical objects that had that gravity acceleration. I looked at like Sedna and Pluto and some other small asteroids, but everything accelerated faster than that. So I don't have any planets or astronomical bodies to compare that to. I thought about just coming up with a theoretical planet size or asteroid size, but the math is messy on that because the volume of a sphere is 4/3 pi r cubed. So if you have two astronomical bodies with identical density, but one is 10 times larger, it'll only have twice the radius, but then you have to take the inverse of the square of that radius to get the gravitational acceleration. Anyways, it's just messy math, so I'm not going to open that can of worms. Quick math on the frame rate here too. This is 10 seconds per 20 frames. I plugged in 10 right there, and that gives me 0.5 seconds per frame. But then I can also do it like this as well. Get that even there. Take our 1/2 AT squared. And here's the deal. I have to come up with a table for the time and the distance that something's going to fall. So I just use the formula, 1/2 AT squared. I plug in time, use the acceleration of 1, and then or 1 centimeter per second squared, and that will give me distance. That's how I got my table here for time. Notice here everything's in 0.5 increments for the time, and that gives me my distance for how fast everything falls. So what I did here actually too is I took the 1/2 AT squared, that's my time, times the number of frames that I'm going to have. I'm going to have 20 frames or 20 increments. So I square the whole thing, I get t squared times 20 squared, I get 400t squared, bring the 2 over. Anyways, that still gives me 1/2 second per frame, and that is the fall rate. So I did that to check my work to make sure everything falls with the same frame rate that it's supposed to, so it matches the frame rate of the bullet traveling up to hit the target. So I just said here time is 0.5 seconds per frame rate, or 0.5 seconds per increment, because that's why it's jumpy with the stop motion for every increment. For anyone that wants to do this at home or for a school project or whatever, just 1/2 AT squared gives the distance. Their acceleration is 1 centimeter per second squared, so it's, the A drops out being, since it's just 1, so it's 1/2 t squared equals distance. This tells me the time in increments of 0.5, because that's how long each frame was, 0.5 seconds per frame. And then the distance, I just plugged in time here, and I got my distances all the way down. But when I'm actually shooting taking the pictures, I need a distance on the hypotenuse of the triangle and a distance on the y-axis. So I use this. I took my y-axis right here, which is I just copied these numbers right here to right here. And then my hypotenuse, the bullet moves at 5 centimeters per frame, 5, 10, 15, 20, all the way down. And it goes all the way to 50 centimeters for the opposite leg of the triangle and 100 for the hypotenuse. Just for fun calculations for gravity here, bullet velocity is 10 centimeters per second. There's the acceleration, 1 centimeter per second squared, which is 1/1000th of a g, or I should say 1/1000th of gravity acceleration on Earth. Since it's 1/1000th, let's take everything up to lifelike or real world situation and see how fast things are moving. Just multiply velocity of the bullet and the velocity of the acceleration by 1,000, and I will get 100 meters per second for the velocity of the bullet, which is also 328 feet per second. That's faster than a modern compound bow. They max out at 300 feet per second, and most are in the 200s. And miles per hour, that translates to 224 miles per hour. So this is on the second run when the gravity was 1/1000th. On the first run, it was 1/500th. I figure there's 2 ways you can look at this motion and this gravity. One way is to say that you're on an astronomical body, like a large asteroid, with 1/1000th of the gravity. But another way to view this is that you're on Earth and everything is just slowed down to 1/1000th of the rate, so you can see it in slow motion. If you want to say that all this is happening on Earth, so that object's flying, that bullet's flying 224 miles per hour, because we scaled up the velocity and acceleration by 1,000. We also need to scale up our distances by 1,000, because if you watch the video again, you'll notice there's quite a bit of drop from gravity. So that means instead of the bullet traveling 100 centimeters, which is a meter, it would actually be traveling 1,000 meters. And that would be the distance to the target, but then the elevation of the target would be 0.5 meters up, which, because that was 50 centimeters, so you multiply that by 1,000, and that will give you 500 meters elevation. But in real life, if you were to shoot something with that velocity, it wouldn't make it that far in our atmosphere because of the drag. Also, notice how I got my numbers. I didn't have to use like the sine of 30 degrees and the acceleration of gravity times that. And that's because I made up my own distances that everything was going to fall. I made up the acceleration. So I didn't have to use any trig in this to get the y velocity or the x velocity. Instead, I started with how long everything was supposed to be in the air, which was 10 seconds. and I just plugged those numbers into the equations and got the results. So yeah, if you ever want to, or I might do this sometime later, plug in some numbers with the trig, like take the velocity of the bullet and get the x component and the y component, but yeah, I figure you don't really need to.